Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be looking at computer generation of random variables. I might actually broaden the title of this lecture a bit and call it the computer generation and manipulation of random variables and random data. What we're going to focus on today is the computer estimation of probability density functions for common random variable types, ones that we already know the theoretical PDFs for. The reason I'm doing that is so that you'll gain some confidence in the techniques that I'm going to be teaching you. You'll trust your results, and later on in your careers when you're working with truly random data that does not have a necessarily well described or well understood underlying probability density function, you can apply these techniques, trust the probability density functions that you will estimate, trust the means, variances, and other calculations that you might do. So we're going to focus on estimating things we already kind of understand, so that later on you can work with truly random data and trust your results. So let's begin. Recall this property from early on in our discussion of probability density functions. The probability that my random variable, capital X, this is my random variable, the probability that random variable, capital X, lies within the range x1 to x2 equals the definite integral of my probability density function for x between points x1 and x2. That's one of the central properties for probability density functions. All right, now think way back into an early calculus class, and I can write this relationship in an estimate form as follows. All right. Here I'm going to assume that delta x is small. And what I'm essentially doing is I'm looking for the probability that my random variable x falls in a small, narrow region centered on x1. I'm going to let x1 equal my bin center, and I'll say more about this in a minute, my bin center, and delta x will be my bin width. All right, so if we were sketching this out, it might look something like this. I've got a bin centered at x1. It's delta x wide, and the peak value is my probability density function evaluated at x1. All right? So now we can rearrange this just a bit. We can say that my probability density function at x1 is approximately equal to 1 over delta x times the probability of lying in a small region around x1. Okay? Now, let's assume that we have lots of data. Imagine we have, that's not a W, ASSUME. Assume we have lots of samples of my random variable x. Assume we have lots of samples of random variable x, and we somehow sort this data in ascending order. Sort the data. Sort the data. And we will find, let's assume that we find little n points in the bin centered at x1. All right? I'm going to assume we've got lots of samples of my random variable x, and I'm going to assume somehow that we sort this data and discover that there are little n samples in the bin centered at x1. I'm then going to apply the relative frequency approach to of probability. And then I can simplify my relationships one further step. So let me begin by writing the last relationship down from the previous slide. We'll say that's the last relationship from the previous page. We're going to assume we've got lots of samples that we sort, and we discover that there are n samples in the bin centered at x1. So I can further simplify this to be 1 over delta x times the number of samples centered in the bin centered at x1 divided by the total number of samples. N equals total number of samples of my random variable x. All right? So we've estimated the probability density function at x1 by finding the number of samples that lie in the bin centered at x1, divide by the total number of samples, and divide by the bin width. We can generalize this a bit. I'm going to generalize this a bit to yield So what I've done here is, let me define some variables here. Each n sub xi is the number of samples in the bin n of xi is the number of samples in the bin centered at x sub I. I'm assuming in this formulation that each bin is equally spaced. All right, I'm assuming that each bin is equally spaced by delta x. Each bin is delta xy. That doesn't necessarily have to be the case. I'm assuming that to be the case here. I typically do in my own work. They're capital M, total bins. Total bins over the range. I'm assuming there's M total bins over the range of my random variable x. And in particular, the summation of k equals 1 to capital M of, n x sub k equals n. So if I add up the number of points in each bin over the total of m bins, I get the total n, capital N, number of sample points. All sample points are accounted for. All right? And I'm sort of tacitly using some Matlab notation here. A one row vector. So make some comments here. All things being equal, what we're doing, my probability density function is estimated probability density function is being estimated by a discrete collection of values So what I've done is I'm estimating my probability density function by a discrete collection of values located, each of those estimated values is located at equally spaced bin centers. Each of those are designated by an x sub I. My estimate of the probability density function generally gets better if F1, my bin width decreases. If we use smaller bins, we'll get finer sampling across my probability density function. It generally gets better if we have a larger number of bins. If we increase the number of bins across our samples of data, we generally get a better estimation. And the more data points, the more values of my random variable x that we have to play with, the better our estimations get. All right? This one row vector in x1, in x2, in x3, all the way out to in xm. This is known as the histogram. That's the histogram of my random variable x. Calculating the histogram is generally the hardest part. Remember, we're starting off with n samples of my random variable x, and the first thing we have to do is sort them into a collection of bins. A bin centered at x1, a bin centered at x2, x3, all the way up to m bins. We have to sort our data and find out how many sample points fall within each of my bins. I then if I'm successful in doing that, I've created what's known as a histogram. If I divide then by the total number of data points that I'm playing with, as well as the bin width, I get an estimate of the probability density function. Calculating the histogram, generally speaking, is the most challenging part. Fortunately, we have Matlab, and I'm going to give you some Matlab-like code to work with. Matlab is very happy to calculate the histograms for you. So here's some Matlab-like code. It's not going to be perfect syntax. Matlab-like code for calculating histograms. If I can calculate the histograms, my life is pretty simple. All right. I've got two different ways to do this. One. First thing I can do is I can define my bin centers up front. Oops. So in this case, I'm going to define my bin centers. First thing I'm going to do is define my bin centers. And then I'm going to let Matlab calculate my histogram. All right. Let Matlab calculate the histogram. All right. X is a vector of data. C is, this is a vector of bin centers. All right. There will be M values there. All right. My vector C will have M values. X is my random data. And I will have N data points in my random data vector X. My histogram will then be M values long. All right. So my N data points in X will be sorted into M bins centered at each of the values in the vector little c. That's going to give me back the histogram, which is the sorted number of points in each one of those bins. All right. Capital N is just then the length of X. My probability density function estimate will be H dot slash N times delta X. All right. This will also be an M point estimate of my PDF. Okay? And then you can plot it if you want. Plot it, C FX. So C is an M point vector. F sub X is an M point vector. Plot that and you'll get your PDF estimate. All right, a plot of your PDF estimate. All right, that's one way of doing it. In this particular case, you pick up front what your bin centers are going to be. You pick your lowest, you pick what the lowest bin center is, X1, the highest bin center is X2, and you specify the bin width, delta X. Matlab's happy to do the rest for you. There's another way. this case, it's a little bit different. Now, m is an integer. My pen quit working. M is an integer, and that equals the number of bins I want to work with. All right, you specify that up front. X is my random data. And of course, there are endpoints. In this case, what you do is you specify how many bins you want and give it the random data. Matlab goes in and sorts. It gives you back m equally spaced bin centers. N equally spaced bin centers over the range of data x. And capital H is my histogram. It's sorted, it's the sorted data. And of course, this is m points long. And likewise, my bin centers, I get m equally spaced bin centers. H is my histogram, and it's also m points long. Still, n is the length of x. Delta x is going to be, for example, C2 minus C1. My probability density function is then, I guess, in Matlab code, I wouldn't subscript it with a big capital X. It'll just be fx. Will be my histogram dot slash n times delta x, and then plot c comma fx. Okay. All right. So my students over time have asked me countless times, Dr. Duncan, how do I pick the number of bins? How do I pick my bin width? How do I pick my bin centers in order to get smooth, accurate estimates of my probability density function? Well, my dear students, this is where a very scientific process of fiddling comes in. Nobody likes to hear this, but it's absolutely true, and it's what I do. You must fiddle with the number of bins, the bin width, and bin locations until your estimate is good enough. I hate to tell you that. I know that's unsettling, but there's really no better way to do it. When I write my Matlab code and I've got random data that I'm manipulating, I sit and I play with it, and I adjust the number of bins, and I adjust the bin widths and the bin centers. I just fiddle with the data until I get a reasonably smooth, accurate estimate. All right. Some other things we can do with Matlab while we're at it. That's supposed to be the word check. A quick check. In Matlab, we can do this. I can do summation that's supposed to be an an asterisk. If you've done everything correctly, remember in Matlab, the summation function is equivalent to the integral function. If I integrate, in effect, my probability density function over the range of values that I have, and I multiply that times delta x, I ought to get 1 back. If I don't have 1 when I perform this function, I did something wrong. So, integrate f of x over the range of values, multiply times dx, or delta x rather. Do you get 1? If you do, good. If you don't, you did something wrong. Now that doesn't necessarily mean that you have a smooth estimate of your probability density function. It just means that you're doing the sorting properly. You're using the histogram function properly. All right, how could we calculate the mean? Using Matlab. Remember, the mean of a random variable is integral from minus infinity to infinity of x. Remember that? That's how we calculate the mean, or the first moment. Using my probability density function estimate, I could do this. M equals sum of C dot star f sub x dot star delta x, and that's how I would do it in Matlab. All right, so in effect, x is estimated by my vector of bin centers. My probability density function is estimated by f sub x. And I always have to throw in that dx. That's my delta x. That gives me my mean based upon my digital PDF estimate for x. I can also calculate the mean squared. Pretty straightforward. Expectation of x raised to the second power is integral from minus infinity to infinity of x squared times the probability density function of x dx. In Matlab, let's just call this M2 mean squared. This will be sum of C dot superscript 2 times dot asterisk fx dot asterisk delta x. That gives me my mean squared. So x squared is estimated by squaring my bin centers. Once again, my PDF is estimated by my PDF estimate, and delta x is estimated by delta x. That'll give me a very good estimate of my mean squared value. All right. And lastly, variance. Remember, we calculated the variance was the mean squared value minus the square of the mean. And using our Matlab estimates, we could do this. We could make a variable sig. And oh, by the way, the standard deviation is just sigma, square root of the variance. In Matlab, we could define a variable sig, meaning sigma, or our standard deviation, and that would be the square root of m2 minus m squared. All right, pretty straightforward. Okay? All right. So the first thing, let's talk about a uniform random variable on 0 to 1. All right? Uniform random variable on 0 to 1. I'm going to assume that I have n of 500,000 points, and I'm going to go into Matlab and I'm going to use x equals rand 1 comma n. All right, rand is the uniform random number generator function in Matlab. What this code gives me is a one row of n random values between uniformly distributed between 0 and 1. Okay? Okay? I decided that I was going to look at 40 bins. The minimum bin was going to be 0.0125. The maximum bin was going to be 0.9875, and that was equivalent to a bin width of 0.025. All right. I calculated using my rand function 500,000 data points. I used one of the histogram sorting functions in Matlab. Sorted into 40 bins, 0.025 wide, and this was my result. All right, this is the result over on the right-hand side. I am going to make available to you a program entitled histuniform.m. It's got all the steps that I use to create the PDF over here. The red line is theory. And the blue line is the estimate. The blue dots, rather, blue circles, is the estimate. All right. Literally what I did was I used the rand uniform random number generator in Matlab, generated 500,000 points, sorted them using the histogram function in Matlab. In this case, I assumed that I had 40 bins. My minimum bin was 0.0125. My maximum bin was 0.9875. I used Matlab histogram function divided by delta x and capital N, and plotted the results in the little blue circles. It's really going to be a whole lot easier if you do what I'm suggesting here and pause this video, download HistUniform Matlab program, and study the code. It's not real complex, but it'll take me 10 minutes to describe what you'll probably be able to figure out in a couple of minutes of observing the code. All right, so please, right now, pause the video and go look at the code and look at the steps that I used. All right. Now I'm going to assume that you have indeed paused the video and studied the code, and I want to take things one step further. All right. Let's see if we can estimate the probability density function for a Cauchy random variable. All right. All right. Let's estimate the probability density function for a Cauchy random variable. So what I'm going to do is this. I'm going to first start with the fact that Matlab is happy to generate data for me that's uniform on 0 to 1. All right. And I am going to find a new random variable y, which is g of x, and generate a probability density function that looks like this. All right, this is a Cauchy, this is the probability density function. That's a probability density function for a Cauchy random variable. All right. So, for this particular problem, I'm going to assume that alpha equals 1 in my probability density function for y. And I know from my previous work that my transformation function y equals the inverse cumulative distribution function for my Cauchy random variable evaluated at x. All right. So we need to find the cumulative distribution function for y and then invert it. All right. Let's do that. I looked that up in an integral table. If I give you a test problem that requires integral tables, I'll provide you the integral tables, okay? Don't worry about that. So performing this integration on further, I get 1 over pi arctangent of y plus pi over 2. And that is just 1/2 times, plus 1/2 plus arctangent of y over pi. Okay? Let's go to the next page and finish this up. So what I have at this point is my cumulative distribution function for y equals 1/2 plus arctangent of y over pi. And remember, what I'm looking for is y equals y let's try that again. I'm looking for a transformation function g, which will take a random variable that's uniform on 0 to 1 and create some new random variable y, which in this case happens to be Cauchy. So what I'm going to do is I'm going to set my cumulative distribution function here equal to x and then invert it and solve for x. All right. So y equals transformation function that I desire, and that's going to be the inverse of that, and that's tangent of pi over 2 times 2x minus 1. Okay, that's our transformation function. All right, and oh, by the way, if we plotted the cumulative distribution function for my Cauchy random variable, I guess that would be y. It looks something like this. Up here is 1. The asymptotically approaches 1. That's a half. And for this one, when alpha equals 1, this is maybe a scale of about 5, 10 here, minus 5, minus 10. Roughly. That's roughly the scale. All right? So, what are we going to do now? What are we going to do now? What we did, what I'm going to do next is I'm going to calculate n points in X, uniform on 0 to 1. I'm going to use the rand n function. I'm going to use rand use the rand function in Matlab to calculate those uniform data points on 0 to 1. All right. I'm going to put those n data points into my transformation function. Put n points in X into my transformation function. This thing, plug it into there, and I'm going to get to yield capital N points in Y. All right? I'm going to create a long vector of data points in X, plug them into my transformation function, underlined in red, and get out n points in Y. Then I'm going to use Matlab's histogram functions, normalize the histogram function against the number of points capital N and the bin width delta Y in this case, and plot the results. Calculate a normalized histogram, plot the results. The results look something like this. All right. Once again, I'm going to give you the Matlab code that I use. It's called histcauchy.m. All right. Alpha was 1. Remember, that's one of the assumptions for this particular analysis. I chose, after a lot of fiddling, until it looked good, I chose a bin width of 0.5. I ended up using 81 bins over a range of minus 20 to 20. Sometimes you end up with an odd number of bins if you are interested in a symmetric probability density function, which includes a bin right at 0. All right, so it's 40 bins to the left of 0, 40 bins to the right of 0, and 1 right at the origin. All right, you a lot of times end up with an odd number of bins when you straddle the origin. As in the first example, I used 500,000 points to calculate 500,000 uniformly distributed data points, uniformly distributed on 0 to 1 using the rand function. Just purely for purposes of clarity, I say I plotted over minus 15 to 15. This curve is actually from minus 10 to plus 10, I notice. I plotted over the range minus 10 to plus 10 because my PDF estimate gets arbitrarily close to 0 way out in the wings, and my peak was kind of skinny and scrunched up. So purely for clarity, I plotted my results from over the range minus 10 to plus 10. So once again, what I really strongly suggest you do is stop the video, pause the video, and go study the code. I've given you all of my Matlab code that will calculate the PDF estimate for this Cauchy random variable. Please do go study that, and when you're done, come back. I've got one more thing to discuss with you. All right, one last discussion, and I'm going to let you go for the day. What if we wanted to estimate the probability density function for a Gaussian random variable? I have a Gaussian random variable and I want to estimate its PDF. What do I do? Now, it's true that Matlab has a built-in Gaussian random number generator. It's this, rand_n, the n meaning normal. Another name for the Gaussian function is the normal distribution. Rand_n will give you Gaussian distributed data with 0 mean unit variance. I should say a Gaussian random number generator. Gaussian random number. I'm having a hard time writing today. Rand_n is a 0 mean unit variance Gaussian random number generator in Matlab. But what if I want to generate Gaussian distributed data with any other mean invariance? We've discussed this a bit before. Let's just remind ourselves what we're doing. I'm going to use Matlab to generate a bunch of data that's uniform on 0 to 1. I'm going to put this into transformation function g, which we know to be the inverse cumulative distribution function for y, and I'm going to get out data that is distributed according to a Gaussian probability density function. Okay? My probability density function equals 1 over sigma square root of 2 pi e to the minus y squared over 2 sigma squared. And the cumulative distribution function that's that. I'm going to invert it by setting this equal to x, and I come up with the following. This is my transformation function. Y equals sigma q inverse of 1 minus x plus m. That's my transformation function. That is the function that will take uniformly distributed data on 0 to 1, x, and convert it into Gaussian distributed data, y, with mean, m, and standard deviation, sigma. And you will also recall that I have previously sent you a Matlab function which will calculate Q inverse. All right? So, what I did is the following. I calculated a PDF estimate for a Gaussian random variable. I assumed for this particular problem that I had a mean of 5 and a variance of 4, meaning that my standard deviation is 2. All right. I assumed that my bin size was 0.2. I assumed that I had 51 bins over the range 0 to 10. I started off by calculating 500,000 uniformly distributed data points between 0 and 1 using my RAND function. And then I used Matlab's histogram analysis function and normalized that with respect to the total number of data points and the bin width, and plotted my blue dots. Blue dots are my estimate of my PDF. Plotted that against the theoretical probability density function, and the curve over here on the right hand side of the page is what resulted. I'm not giving you the code for this one. You are going to write the code for me as a homework problem to generate just exactly this curve, the curve on the right hand side. You're going to write that code to me, or for me, and submit that to me for grading. I do want to point out a couple of interesting points here. I make a statement here. Notice the PDF estimates at y equals 0 and 10 in this case. That one and that one. Those 2 points exist because when I calculate my 500,000 points uniform on 0 to 1 and stick them into the transformation function back here, this transformation function does not guarantee me that all of the data points in y exist between limits 0 and 10. Remember, the probability density, the Gaussian probability density function extends from minus infinity to plus infinity. So all of the points in y that are above the value 10, they end up being represented in the histogram estimate at y equals 10. Likewise, all of those points in y that are less than 0 end up in the histogram estimate at y equals 0. All right? There's a couple of ways around that. If those 2 points are unsettling to you, what I could have done is use 53 bins. I could have used 53 bins. And my minimum bin could have been minus 0.2, and my upper bin could have been 10.2, and I still could have plotted over the range 0 to 10, and those two outliers would have just simply disappeared. If I had extended my bins down 1 point further, I would have had a point there, and maybe a point up here, and a point here, and maybe a point up there. If I plot over the range 0 to 10, I wouldn't have had these funky outlying looking PDF estimate values. All right, that's a lot to digest, but that's all I have for you today. Please make sure you study the Matlab code that I've given you. You can go back and review this video a couple times if you need to. If you have any questions about how to write the code for estimating the Gaussian probability density function, please do let me know. As usual, if you have any questions, let me know at your earliest convenience, and I will attempt to answer them as fully as possible. That's all for today. Bye-bye.